Glory, ma'am.
Hello?
Shall we start the meeting, ma'am?
Yeah.
A very good morning to all. I welcome you all to this two-day webinar on MÖSSBAUER spectroscopy, elucidation of magnetic compounds in biological system. At this juncture, I thank the Lord Jesus Christ for giving us strength to arrange this webinar. Now, Dr. Glory, Head and Associate Professor, Department of Botany, St. Mary's College, Autonomous, will deliver the welcome address. Over to you, ma'am.
Distinguished resource person, Reverend Sister Principal, Reverend Sister Secretary, Reverend Sisters, colleagues, and all the participants. Very good morning, one and all. Advanced information technology confirmed learning has no lockdown and it breaks spatial and temporal barrier in education. Department of Botany, St. Mary's College, one of the leading departments, has privileged to make use of such facilities and technologies so that has arranged this webinar with eminent speakers. I'm so fortunate to welcome and introduce the chief speakers to all the audience. Dr. Sahayat Sadish, Dean of Biological Science, St. Joseph's College, an eminent professor, has accepted our invitation to give away the inaugural address. He has vast academic acclaim and achievements. He has conferred his doctoral degree from Bharatidasan University, Trichy, for his studies in graphite. He is a great teacher with 25 years of teaching and research experiences. His expanded research pursuit made him to produce nearly 35 research articles and publish 7 research papers in reputed journals with high impact values. He has produced 5 PhDs and guiding 6 scholars presently. He has organized several conferences, workshops, symposia. Besides his teaching pursuit, he has held so many positions in academic line over nation. His enriched knowledge made him to be the author of 2 books and author of many chapters in various books. We are really fortunate to have you, sir, for this meeting and to deliver the inaugural address. On behalf of the management, faculty of Department of Botany, and student, we extend a warm welcome to you, sir.
Thank you. Thank you.
It's my great pleasure to welcome Dr. Justin Josephus, Associate Professor, National Institute of Technology, Trichy. He's a great academician, conferred his doctoral thesis on nanocrystal magnetic material from University of Madras and pursued his postdoctoral research in Tohoku University, Japan, and continued his research in National Institute of Technology, Trichy. He has published more than 50 research articles in the international journals with high impact values. He has undergoing and has also completed one project on hard magnetic materials. His current research interest is in enhanced magnetic properties and elucidation of magnetic compounds in biological system. He has pending patent related to temperature sensors using magnetic materials. In that, he is undergoing a project. Certainly, we are proud to have you as a speaker of the two-day national webinar. It is my pleasant, on behalf of the department, once again, I extend a warm welcome to Justin.
Thank you, Doctor.
My pleasant task to welcome our principal, Dr. Sister Lucia Rose, who is a force for organizing this seminar. My special welcome are due to Sister Shibana, Vice Principal, Dr. Sister Joyce, Director of Self-Supportive Courses. I warmly welcome all my department colleagues and my dear students and all the great participants. Hope the 2 days webinar would be useful and meaningful. Thank you, Anand.
Thank you, ma'am. Thank you for your warm words of
Thank
welcome.
you. Thank you.
Now, I would like to call upon Dr. S. Sagaya Satish, Dean, School of Biological Sciences, St. Joseph's College, Trichy, to deliver the inaugural address. Over to you, sir.
Respected Principal Sister Lucia Rose. Ma'am, one doubt, can you see my image, video?
Yes, able to hear.
Video also? Because I can't see my video. Okay. Let me start. Can
Yes,
you
sir,
hear
you
me?
can start, sir. Yes, sir. We can hear, sir.
Okay. Respected Principal, Sister Lucia Rose, esteemed the Head of the Department of Botany, Dr. M. Glory, Speaker of the Day, the Chief Guest, Dr. R. Justin Josephus, and Faculty of the Department of Botany of St. Mary's College and the Faculty of other Department of St. Mary's College, and my dear participants, good morning to you all. First of all, I would like to thank the management of St. Mary's College and special thanks to Glory Madam for giving me this opportunity to give an inaugural address for a wonderful event. I feel honored to be a part of this webinar. The topic must be a spectroscopy elucidation of magnetic compounds in biological system is a very appealing and very interesting topic. I congratulate the management and the Department of Botany for choose this topic. As you know, due to the COVID-19, the pandemic, the world get freezed. The people of the whole world is trying to save their life by taking precautionary measures and also trying to save the infected people. This is going on one side, but in other sides, the academicians are organizing these type of programs to make the students to in touch with the academics. So almost we crossed 60 days in the lockdown period, almost 2 months over. So by this platform, we can create some awareness or inculcate some knowledge in advanced studies, advanced subjects to the young mind. So this is a great attempt by our institution, the reputed institution, St. Mary's College. And this topic is very interesting one. You know, in the research in biology, have a breakthrough after the invention of microscope. After the invention of microscope, only the microbiologies and the discovery of penicillin, like that, the drugs, medicine, everything. The research is flourished after the invention of microscope. Like that, the spectroscopic studies after the advent of this technology only, the mankind started, the researchers, the scientists started to elucidate or know the chemical structure or identifying the different compounds in the living entity. For example, the plants, the small herbaceous plant can develop or produce more than 50 different kinds of secondary metabolites by the different discriminative pathway from the primary metabolites. So enumeration of these compounds and characterization of the compounds can be only done by the many spectroscopic studies, starting with the USFTAR and the recent LCMS and GCMS, isn't it? So this MÖSSBAUER spectroscopy only after the Rudolf MÖSSBAUER, he is the only person he invented, discovered the MÖSSBAUER effect. And he got the Nobel Prize for this in physics in 1961 also. So the elaborate detail will give you by our chief guest, Justin Josephis. And another one, the nano is, one of his topic is the nanoparticles. This is my interesting topic because I am indulging in I am allowing my students in nanoscience. I will give some informative small idea about the nanosciences, isn't it? So first, this concept was introduced by Richard Feynman. When he was delivering a talk about the top-down nanotechnology in a conference. In the title, there is plenty of room at the bottom. He only introduced this concept, the nanotechnology. And this term is coined by Toru Nanaguchi. Okay. So the students, what is nano? What is nanotechnology? What is nanomaterials? A simple basic thing is the whole entities or things in the world we can categorize into three on the basis of the sizes, no? Macro, micro, and nano. Macroparticles, microparticles. The size above 1 millimeter on macroparticles, and the size between 100 nanometer and 1 millimeter, that is microparticles. Those materials below 100 nanometer. So any objects less than 100 nanometer, we can say it as a nanoparticle. Okay. So the nano size, the the recently, this decade only, this science emerged. So this nanotechnology have vast scope, vast application. The field of chemistry, biology, physics, material science, energy, even the medicine, electromagnetic, biomaterials, energy. So lot of things are there. Nanofabrics, the different applications are cosmetics, bioenergies, medicine, energy, nanofabrics also. In this we can, I want to say one thing, antimicrobial fabrics. When I was working in the St. Service in 1994, my brother brought me socks, nano socks from Bangalore. That is 15 or 14 years back. Nano socks. In the nano socks, you can see the coating of the silver nanoparticles. Silver coating in the sole. You can see. Usually our boys, as soon as they come back from the school or college, as soon as they enter the house, when they remove the socks, we will feel unwanted odor, unpleasant odor. நம்மளே நினைப்போம் என்னடா இது வீட்டில் ஏதாவது எலி செத்துட்டா அந்த அளவுக்கு இருக்கும். This is because these children, they use or wear the socks in the wet condition. So what will happen? The colonies, the microbial colonies will develop in between the fingers of the legs. So it will create a odor. But if you wear these nano socks, it prevents the production of these colonies. So this is one. And bulletproof, lot of, even in making the paint. So these reduced size particles have much application. Why? When you reduce the size, easy to handle, and the action spectrum of the surface area will increase in the nanoparticle. So the active spectrum will be getting increased. For example, in the botany, we can say, one quote is there, reduction is the sign of advancement. Reduce size is the sign of advancement. When you reduce the size, even in the human we can compare. When a tall person traveling in the bus, you will find very difficult to sit. The front seat will hit his knee. But The person with the short stature, he will happily sit. So sometimes the size, the reduced size will give some advantage over the size. Like that, the reduction in the size. For example, if you reduce the size of the plastic, the property of the plastic, it will start conducting electricity. So the change in the size give a change in the property. So this change of the property we are adapting or exploiting for discover the drug, everything. So in the present scenario is a need of the day, we have to find out the medicine. Even we couldn't find the medicine for AIDS virus, but the COVID-19, all the research centers of the whole world are trying to produce a vaccination, but not yet. So if you, one side, even the research, the biological research, the medical science is going, developing because of the research aptitude of the humankind is enormously enlarged, but sometimes we could see the nature is one step ahead of the research. So we should be careful. The research should be the essential need. So I'm not away from the topic. So the final words I want to say, the researchers, the research, every country should not beyond the nature. For the luxury, the nature, by this exploitation of the nature, the greedy attitude of the humankind, the whole environment get spoiled. The present, the people, the advanced people, they won't mind about the environment. They are thinking about settling in another planet, but they are spoiling our own native planet. This is not the way. So the students, nowadays, because of the COVID-19 pandemic, everybody getting fear. They are inside the home. In WhatsApp, I could see the joke that a person fainted and admitted to the hospital. And the doctor said, no problem, you don't have corona. You only had a heart attack. Oh God, he said, thank God. So people get fear because of the COVID-19 pandemic. And our research, especially the botany students, keep in mind, we should protect our environment, protect our native planet, Earth. Will you use any technology using electricity, you minimize it. The biofuel also we should minimize it, so we can prevent the enormous emission of the gas, chlorofluorocarbon into the air. So my humble advice for the students is keep it on mind, don't waste anything, don't go beyond the nature, go by bicycle like that, isn't it? But I couldn't see the image of the video of mine, so I tried to speak like this. And once again, I thank Glory Madam for giving me this opportunity. I hope most of the students from St. Mary's College, botany students are there. I want to say one thing. You are very blessed, because once I was when I was attending a board of studies meeting with Glory Madam in the Holy Girls College of Nagarkoil, I could see her depth knowledge, both in advanced as well as the classical, basic, and fundamental science. It's a very good teacher. Really, I say you are very blessed, very good teacher, and she gave me this opportunity. And I thank the principal sister, the management, and the organizing secretary, the head of the department, Dr. Glory Madam, for giving me this wonderful opportunity to say a few words and to wish this webinar. So I wish you all the best. Have a nice 2 day for this seminar. Thank you very much.
Sir, for your greetings and for giving brief introduction on today's topic through your inaugural address. I am sure that all the participants have taken note of your suggestions. Thank you, sir.
Thank you, madam. Thank you.
Dear participants, you can post your question in the chat box at the end of the session. Otherwise, raise your hand. We will allow you to ask questions directly. Now, I hand over this session to Dr. Justin Josephus to deliver his lecture on magnetic materials in Earth and Life Science. Over to you, sir.
Thank you. I thank the organizing committee for arranging this lecture in spite of a lot of difficulties. I also understand that many participants may be having issues with the connectivity and other things. But I will also try to address.
Justin, sir? Justin, sir? Unmute your mic, sir.
I am using the other mic. Please enable the cam mic. Hello? Can you hear me? Hello? Please enable the cam mic. Hello? Yeah, can you hear me?
Yes, sir. Yes, sir.
Okay. Thank you for giving an opportunity. So I will address this person that is from biology background also. So MÖSSBAUER spectroscopy, the name itself implies that it is somewhat physics related. But I understand that most of you are from biology background. So in that sense, I will try to go slow through the physics part, because many biologists may think that physics is not required, but indeed it is required, as you see from this presentation. So I will address fundamentals and a few examples in biological system and earth system. So today's session will be mostly on fundamentals. And if there are any questions at the end of the session, we can have, or we can continue it tomorrow also. So today we will focus on the fundamentals and few examples. So if you just see this slide, do you have any idea about what it means? Okay. I think many of you may not have any idea about what this means, But at the end of the presentation, if you are able to understand the meaning of these two, then this webinar will be a success. Okay. So the contents are as follows. First, I will just discuss about magnetic materials, not elaborate, but very brief. I will also discuss about MÖSSBAUER fundamentals, not with many equations, but from the general audience, okay, to satisfy the general audience. And why we require this fundamentals is like we should know what are the materials you could characterize and how you could characterize. So to focus on those aspects, I have included MÖSSBAUER effect fundamentals. And next one is, what are the properties that could be studied using this MÖSSBAUER effect? So that can be understood from the MÖSSBAUER parameters. So that is also included. Then finally, I have included few applications. So in this 1 hour lecture, we could not include all aspects of MÖSSBAUER spectroscopy because it is a vast sea. But anyway, I will try to give you an overview or an introduction about this technique in this presentation. So about magnetic elements, you could see this periodic table. In the whole periodic table, there are only 3 elements that are ferromagnetic. Those 3 elements are iron, cobalt, and nickel. So you see that there are other elements which are having negative susceptibility values, negative values. So those negative susceptibility values, those materials are diamagnetic materials. So diamagnetism is defined from this susceptibility relationship, chi equal to m by h. So if you apply a magnetic field, the magnetization will be negative. So that is negative susceptibility. And you see this side, most of the materials, they are paramagnetic. They have positive susceptibility, chi, but they don't have very, very large susceptibility like the ferromagnetic elements, iron, cobalt, and nickel. Okay. So why these materials are showing negative susceptibility is because if you take a shell, if you put 2 electrons in the shell, so 1s2 shell, you have 2 electrons, and you have, according to Hund's rule and according to Pauli's exclusion principle, you cannot have all the electrons in the same energy state. So you have one spin up and another spin down. So magnetic moment is proportional to the unpaired spins. So if you have unpaired spins like here, 3D, so you have 5 electrons, all the 5 electrons are up. So in that case, you have a magnetic moment. That is the case with iron, cobalt, and nickel. Whereas if you have all the shells, all the spins, which are paired like this, up, down, and the net magnetic moment is 0, then the magnetic moment will be 0. They will exhibit diamagnetism. So that is the basics. So with this one slide itself, I have tried to explain you the origin of magnetism in most of the materials. And among these 3 materials, iron is the one which is found almost everywhere. So that has some universal history. That is right from the Big Bang, we can explain why iron is more stable. So you see here, this next slide, our universe began with this Big Bang. some 13.8 billion years ago, right? So during that Big Bang time, you had only two elements, hydrogen and helium. Okay. And when the universe cooled, at that time it was very, very hot and very high energy. And when the universe cooled, all the galaxies, stars, everything began to form. And the hydrogen helium got converted to other elements through nuclear fusion. Okay. So that's how we got all these elements in the periodic table. And all the elements are not equally probable. That means, no, you cannot get all the elements of equal proportion out of this nuclear fusion. So you have certain elements, oxygen, carbon, nitrogen, sulfur, magnesium, aluminum, silicon, and iron. So till iron, you can get through fusion. So then when your universe is very hot, you have this atomic state, and as it cools, and when you are moving to a temperature below the melting point, then you get solid iron, or iron can combine with the oxygen and form iron oxide. Iron can combine with the silicon and oxygen, and you can have other silicate phases. So these are the components of our Earth. So the Earth has all those elements which I have shown here according to the proportion showed here. Okay. So our solar system, it began around 6 billion years ago. Okay, it is not exactly 6 billion. 6 billion years ago, there was a cloud, okay, which has all these elemental constituents. What I have told you, these elements were formed through nuclear fusion. And as this temperature decreased, what happened is, no, these elements combined together and they formed a disk. And that disk is what we say as the solar system that formed around 4.6 billion years ago. Okay. So as the universe, as our Earth formed along with the solar system, and when it began cooling, you see that from 4.6 billion years, you see that life form, they began. Okay. So most of the life, they began after the great oxidation event that happened 2.5 billion years ago. Okay. So you have mostly iron, which is formed due to the nuclear fusion. And once Earth began, this iron combined with the oxygen due to the oxidation event, and you get iron oxide in your soil. So if you are seeing the red soil, it is iron oxide as a result of the oxidation of iron, which was formed out of nuclear fusion in the stars. Okay. So our human being, if you see, it is at the bottom end. No, they are very, very recent phenomena, less than a few million years. Okay. So what I want to say here is, no, the iron is an important element, okay, which is part of the Earth and which is also part of the living system, which I will focus in this talk. Okay. So let us go from the Earth to iron in our human body. So if you see our human body has hemoglobin. Of course, it has iron. You see here on the right side, iron. So that is surrounded by the heme protein. So this iron is in +2 state, and in our body, 66% of iron is present in the hemoglobin. Then we have around 10% of iron in myoglobin. It is also similar to this iron heme. It is only 10%, and that is also in +2 state, +2 divalent oxidation state. Okay. Then we have iron as ferritin or hemosiderin, where iron is present in the +3 state or the trivalent state. You have other enzymes and proteins that is only 1%. So in biological human body, 66% red blood cell, hemoglobin, so that is the iron which is present. And hemoglobin, it is produced in the bone marrow, as we see at the bottom of this slide. And from that you get red blood cells, and in the red blood cells we have not only hemoglobin but also other blood components, but we will focus on the hemoglobin here. So hemoglobin structure is shown here, that is ferrostate, Fe2 plus, and the ferritin is shown as a sphere here. So that there inside the ferritin, that is the protein shell, inside that we have ferric ion, Fe3 plus ion. So that is 23% present in the human body. So this is the status of iron in the human body. So you have to be very careful here, because if you are anemic, then iron content is less. Okay. So then hemoglobin content, so when you go for a blood test, people will take for hemoglobin test. So that means the iron which is bound to the heme, so that is only tested. So that only gives you the red color. So you have this hemoglobin and you have this myoglobin that is present in the muscles. Okay. And ferritin, that is present in the liver, and it is a storage iron. Okay. So in this, from this slide, you see that iron is an essential component in human body. Iron is also an essential component in the earth. Okay. Because unless you have iron, you cannot have this iron in your body. Okay. So with this in mind, I will go to the MÖSSBAUER effect. So introduction to MÖSSBAUER effect. Why? Because I am giving an introduction about iron, because MÖSSBAUER spectroscopy is an essential tool to detect iron. So it can detect iron present in any form. Okay. So then we should know what information we can get using MÖSSBAUER effect. So in that aspect, we should understand the phenomena of MÖSSBAUER effect, briefly about MÖSSBAUER instrumentation, and about what are the parameters which you can obtain from MÖSSBAUER effect. Without knowing this, you will be only staring at the spectrum without knowing what to do with it. So you may get a spectrum somehow, but you have to interpret that spectrum. So if you want to interpret that spectrum, unless knowing these fundamentals, you cannot proceed further. But you will see that mostly around 40% of MÖSSBAUER work was done with biology. So that means the Western biologists, they are employing MÖSSBAUER effect in a prominent way to analyze iron. So we will see how the spectrum look like. So as introduced by the inaugural address, it was discovered by Rudolf MÖSSBAUER, a German scientist. He was very young at that time. He was doing his PhD. So this effect came as a result of his PhD work. So if you see the MÖSSBAUER spectrum, you will see only 3 types of patterns: a singlet, that is 1 line, a doublet, a 2-line pattern, or a sextet, that is a 3-line pattern. Now, why you get this singlet, doublet, and sextet, I will explain to you. So in the x-axis, what you have is velocity, relative velocity, and the y-axis we have transmission. So what is relative velocity? I think now you may not be able to follow it, but I think I will explain to you what are those at the x-axis and how we get this singlet, doublet, and sextet, so that you can interpret the spectrum if you are using this, or if you are an educationalist, you can explain this spectrum to students while teaching. If you are a student, you can understand this and you can read papers, you can read the books related to MÖSSBAUER spectrum in a confident manner. So now a little bit of physics. I will go to a little bit of physics. See, you have atoms, and everyone know, like, no, atom has nucleus, it has electrons. Okay, and if you take iron, there are 26 electrons as well as 26 proton, and you have iron which has protons as well as neutrons. But in MÖSSBAUER spectroscopy, we are going deep into the nucleus. Okay? So MÖSSBAUER spectroscopy is a nuclear technique. So most of the techniques which you people may use, all are mostly they may be electronic techniques. Okay. So whether it can be X-ray diffraction or other spectroscopy, UV, FTIR, those are not nuclear techniques. But this is MÖSSBAUER spectroscopy is a nuclear technique. So like you have in electrons energy levels. So you have energy levels, first energy level, second energy level, third energy level, fourth level. So likewise, nucleus also has energy levels. So if you are having one electron here, and if it comes to the ground state or below state, it will emit a photon. Okay, so this photon will be of low energy if it is an electronic transition. That is, if the electrons are transitioning from higher state to the lower state, the energy will be less. So that means, like, you may see light photons. Okay, it can be red color, blue color light, or it can be slightly invisible light like UV or IR, but they are low energy. If you go to the nucleus, there also you have energy levels. So from one energy level, it comes down, emitting photon of higher energy. So in iron, we have isotopes. So this isotope, iron isotope, it has a lot of energies, but we are using only this energy, that is 14.4 keV, kilo electron volt energy. That transition only we are using to analyze our spectrum. Okay. So this isotope, iron isotope, I hope you understand what is isotope. I may not be going too much elementary. So if you have an iron isotope, there may be different isotopes. It can have same proton number but different neutron number. That are isotopes. So if you are having iron, the normal iron which you see everywhere, that is iron isotope, that is Fe 56. The mass number is 56. But in addition, we may have an iron isotope which may have 57, mass number 57. That is very small quantity. Okay. So you have around 98% of 56 and 2% of 57. So that isotope is only sensitive to MÖSSBAUER effect. So that is why I have to emphasize here that you need iron. In that iron, we need iron 57. That isotope should be present. Okay. So now, so when you have this energy, I told you there is energy which is coming out from this transition, 14.4 keV to ground state. And when you are taking this energy, so this is coming out now. So this energy, if you are taking this energy and making it to hit on your sample. Okay. So how this is coming, this energy is coming, this is coming from the 14.4 keV transition of the iron 57 isotope, which I have told you, that is only around 2% of the quantity present in the normal iron sample. So when you have that gamma ray which is coming out of that iron 57 isotope, and if you hit it on your sample, if your sample is also having the same energy, ground state and the excited state, your sample is also having the same energy, then it will undergo absorption. So remember, here we have emission and here we have absorption. Okay. So there will be emission and absorption. Resonance will happen when your sample is having the same energy like the emitting energy. I hope this is very clear. So MÖSSBAUER effect is a resonance effect. So if your sample is having the same energy like the isotope which is emitting gamma ray, then that will give you a spectrum. What type of spectrum? We will see. So, but there is a problem here. Okay, there is a problem here because now once you have the emission of energy, okay, once you have the emission of energy, what happens is the physics principle comes into picture. Recoil. Now you see here, recoil. So once you have a bullet, which is if you shoot a bullet, the gun will recoil, right? So that is conservation of momentum. So you have high velocity bullet which is coming forward but with the lower mass. So the momentum should be conserved. So mass into velocity. So what will happen? Less velocity gun will go backward, less velocity but heavier mass. So there will be conservation of momentum. So similar thing happens at the nuclear level also. So when there is an emission of gamma ray, there will be recoil. Due to that recoil effect, there will be energy loss. So as I told you previously, there will be resonance only when the energy is equal. Emission energy and the absorption energy, both of them should be equal. Then only you will have resonance. But here, due to recoil, the energy is lost. Okay. So here is what MÖSSBAUER did in an exciting discovery. So in order to minimize that energy, so what he put is, he put the nucleus in a matrix. Like you have a small gun which is having lower mass, but imagine that gun is tied with a very strong metal frame, then the whole mass will be larger. Okay, so a free mass of a gun will be smaller compared to the whole mass of the metal frame. So likewise, he put this nucleus in a matrix, that means a solid. So this, let's say, no, this is a nucleus, the gray colored one. So that he put in a matrix, that is the orange colored one. So now the whole mass is taken care of by the matrix. So you see this equation, the recoil energy is given by ER equal to E gamma square, gamma ray energy, E gamma, by mass of the nucleus. Now when you put the, replace the nucleus with the matrix, the mass becomes the matrix mass. So into C square. So you see recoil ER is inversely proportional to the mass. So if you have only one nuclei, then what happens now? The mass will be very small. But if you put the same nuclei in a matrix, that mass becomes very large. So then the recoil effect is eliminated almost. Okay. That is what he did. So now the whole energy is available without loss, without recoil loss, for absorption by your sample. Okay. So now you can go for MÖSSBAUER, but there is a problem now here. Okay. So you are having now see that now the 14.4 keV energy is stable without recoil loss, because now we have eliminated recoil by putting a whole mass. But we, in the process, it is not so. As we have seen earlier, that you have hemoglobin, myoglobin, you also have ferritin. All the iron are same? No. One is in ferrous state, surrounded by heme protein, and another is in a cage, and it is in a ferric state. So that means the energy levels are varying. Okay. So in that case, you cannot reach this energy with the smaller energy. You have a higher energy in your sample, which cannot be reached. So what MÖSSBAUER MÖSSBAUER did was like tuning the energy. How to tune the energy? So let's say now if you are having an ambulance which is coming forward towards you, what will happen? The siren will be increasing its frequency. So that is Doppler effect, which we have studied in the lower class. So you can, when you are increasing the frequency, means increasing the energy. And when the ambulance is moving backward like this, or moving far away from us, then decreasing the energy. So what you have doing is increasing the energy through forward motion and decreasing the energy through moving away from us. So that is Doppler effect. So what MÖSSBAUER did was like he moved the sample absorber, that is the gamma ray emitting source, towards the sample. So then the frequency increases, then it matches with our sample frequency at some position. And that was what. So what MÖSSBAUER did, he eliminated the recoil, he adjusted the sample energy, okay, by moving the Doppler effect phenomena, by using the Doppler effect phenomena. And that's how you can match your sample energy, okay, with the MÖSSBAUER energy. Okay. MÖSSBAUER energy means the energy which is coming out of the isotope transition. Okay. Now how they did is like you have this absorber is nothing but your sample. So suppose if you are having biological samples, then you prepare that sample, that is then absorbed. Okay. Then we have S as the source. Source means what? I told you, the gamma ray which is coming out. So that is the source. So now we have to match the energy of your sample. So for that, we have to use back and forth motion. That is the ambulance effect, which I have told you. So that was done by the transducer. So the transducer will move back and forth, back and forth. So you are having a forward velocity. That is when it is coming towards the absorber, towards the sample, it is the velocity, positive velocity. And that is achieved by the transducer. And when your sample is moving away from the absorber, backward velocity, negative velocity, that is you are reducing the energy. So if we don't know the state of your sample, it may be low energy or it may be high energy. So, but if you are making forward backward motion like this, at some energy it will absorb. So at some energy which is matching with the resonant energy, at that energy it will absorb. So that is how this instrumentation will help you. The detector will detect the outcoming energy, that is the energy which has been absorbed. And all this electronic system, we need not worry too much about it. We have to only understand this three major part: absorber, source, and the transducer, to achieve energy resonance. Okay. Now, what are the elements which can be studied using MÖSSBAUER effect? Undoubtedly, you can study this iron and some other elements like tin, antimony, europium, dysprosium. Why only certain elements can be studied using MÖSSBAUER effect? Because we have to get recoil free energy. So recoil ER is proportional to E gamma square by 2 MNC C square. So you have the E gamma ray energy that can be got only in few of the elements, and we should have sufficient isotope. So these considerations make only few elements that can be studied, and iron is most extensively studied. So that is why this talk we shall focus on iron. So now you see the characteristics of iron. So the gamma ray energy is 14.4 keV, kilo electron volt, and half-life, since it is a radioactive source, the half-life also matters. How long we can use that isotope? It's only 270 days. After that, it will reduce the lifetime, and natural abundance is 2.19%. As I told you, 100% iron is not in the form of iron 57, but iron 57 is only the isotope which can be studied. So you have 2% of iron 57, and that is why iron is extensively studied. But if you see some nickel isotope, let's say nickel isotope 1.7 hours, by the time you buy the isotope, and when it reaches our lab in here, considering all the restrictions and other things, it will be dead. Okay. So you cannot have an isotope which is having lower lifetime. Okay. And if you see that iodine 129, abundance is 0. So it is not at all sensitive. So there is no isotope which can be measured using iodine in the natural system. So that also cannot be measured. So you have all this makes only few elements. So I hope now you have understood why MÖSSBAUER effect is most prominently used for studying iron. Okay. So because of the ease. Now, what are the parameters? What are the parameters which can be obtained from the MÖSSBAUER effect. What are the characteristics which you can study from MÖSSBAUER effect? That we will see here. So MÖSSBAUER effect characteristics are isomer shift, quadrupole splitting, and hyperfine splitting. What is isomer shift? As I told you, MÖSSBAUER effect is a nuclear phenomena. So in your nucleus, the changes in the electron charge density can be measured using MÖSSBAUER effect. So the changes in the electron charge density will be manifested as change in the size of the nucleus. So you have a nucleus which may be smaller in the ground state and larger in the excited state, or other way also. It can be larger in the ground state and smaller in the excited state. So this changes in the nuclear size, how the size will change due to the electrons charge distribution. How the electrons charge distribution will change according to your element. Okay, so let's say like now if you have a neutral ion, your neutral ion means no, the number of electrons in neutral ion 26. Okay, so now if you remove 2 electrons, from 26, it becomes Fe2 plus, isn't it? When you have Fe2 plus, the electron charge density is also now reducing. Now you remove one more electron, Fe3 plus, then that electron charge density is also reducing. So that will be sensed by the nucleus. Okay, so the change in the size of the nucleus will give rise to isomer shift. So that can be measured. So isomer shift will give you a type of bonding, meaning like no, whether your ion is in a lattice with some other element, okay, like carbon, whether it is bound to symmetrically carbon, or whether it is bound to silicon. So likewise, no, we can find the type of bonding. Charge state means no, whether it is neutral ion or ferrous ion or ferric ion. So Fe2 plus or Fe3 plus, so that can be found, and also the d electrons also, right? So if you are having more d electrons, the s electrons, no, isomer shift is a measure of s electron density at the nucleus. So if you have more d electrons, that will prevent the s electrons from coming inside the nucleus. So that also can be measured using this isomer shift. Now you have this isomer shift data. So from this we can easily see, you know, what will be the isomer shift value for ferrous ion, ferric ion, ferrous high spin, ferric high spin. And you see here in the x-axis, it is given as millimeter per second. That means no velocity. I told you what is the reason for plotting in velocity, because we have to give Doppler effect to match the energy, isn't it? So that is why now we are giving it in the form of energy. Okay, energy manifested in the form of what? Manifested in the form of forward motion, backward motion. So like no, if you are having positive velocity, meaning like no higher energy, negative velocity means lower energy. Okay. So now the second parameter which you can get is quadrupole splitting. Okay. So now we have the nucleus, let's say here, and if it is surrounded by symmetric charges, symmetric electron charges, then the shape of the nucleus may be symmetrical. What is shape? Spherical. Now let's say if you are having a one side push or push and pull by the charges. Now if you are one side pull by charges, then the shape will be changing. So that will be measured by MÖSSBAUER effect. So isomer shift, size change, quadrupole splitting, shape change. So if you are having quadrupole splitting of 0, then the shape is sphere. Quadrupole splitting is non-zero, means the shape is not sphere, it is asymmetric. So that can be also measured. Okay. So this is how the spectrum looks like, quadrupole splitting, because now you have the ground state here and you have the excited state, and the nuclear excited state is now split into 2 energy levels, and there will be a gamma ray transition between these 2 energy levels. So these 2 energy levels will give rise to, there are 2 possibilities, right? One from here to here and another from here to here. So these 2 possibilities will give you a two line spectrum. And you see here in the x-axis velocity, implying that one of the transition is in the higher energy side, more than 0, higher energy side. Another one is in the lower energy side. So you see that there will be splitting. So the ground state, spherical, excited state, non-spherical. So what happens now? There will be a transition from the ground state to the excited state. So if there is no splitting like this, then you will have a single line, only one line. That is isomer shift alone. But now you have a quadrupole splitting, which is 2-line spectrum, and also the middle point, this midpoint is not exactly 0. That means there is isomer shift. Isomer shift means shift from the 0 energy position. So you are having a positive isomer shift, that is the midpoint of this doublet has been shifted. So the distance between these 2 endpoints, that will give you the measure of quadrupole splitting. Please remember this point, very important point. So if you are having a large distance, splitting distance, meaning a large quadrupole splitting. Large quadrupole splitting, how will it occur? Your nucleus is entirely non-spherical. How will the nucleus become entirely non-spherical? There are some other electronic forces which are pulling the nucleus. So your ground state environment has changed in your sample. Your sample is in a different chemical state. So that will give you a large quadrupole splitting. Along with that, isomer shift is changing, means the s electrons and density of the nucleus is also changing. Okay. Now one more parameter I will discuss, that is the hyperfine structure. With that we will go to the application part after completing this. So here hyperfine structure means I told you there is a splitting when there is quadrupole splitting, when there is an asymmetric shape change. Here there will be a splitting when there is a magnetic field. So that is hyperfine splitting. So in the ground state, the previous slide we have seen, previous quadrupole splitting slide, the ground state is not split because now the ground state is spherical. But here we see that the ground state is also split. So you have 2 splitting. So I am not going into the selection rules and other physics related thing, but just understand the origin of the spectrum, how we get singlet, how we got doublet, and how we got sextet. Okay. So the sextet is we got because of the transition from here to here, that is one state to another. So there are many possibilities, of which the selection rules allow only few possibilities. Selection rules are given here. So you have 6 transitions, and little bit of quantum mechanics is required to understand the intensity ratio, why this is 3:2:1, likewise, so that we are not going deep. So you have 6 transitions. So that 6 transition will give rise to a 6 step. So now you have understood this 6 transition happens due to magnetic field. That means if your sample is magnetic, what is magnetic? Means like, no, it is ferromagnetic, ferrimagnetic, or antiferromagnetic, then the hyperfine field structure will evolve. Okay. So if your sample is in the paramagnetic state or diamagnetic state, you will get only a singlet or a doublet. So you get a sextet if your sample is ferro, ferri, antiferromagnetic. Okay. So with this, we will move on to the next part, that is MÖSSBAUER spectroscopy in biology, the applications of MÖSSBAUER spectroscopy in biology. I will focus on hemoglobin because no, most of you are, especially women, so they may encounter this type of anemic blood loss. Blood loss will result in anemia. So then we need to enrich your iron. So you may immediately go to the doctor, and doctor will prescribe some iron tablet for you. Okay. So anemic people, so they have to enrich the iron content in your body. So hemoglobin plays an important role, so that you people can take precaution. Okay. So hemoglobin. So what I have introduced you about fundamentals, basic fundamentals about MÖSSBAUER spectroscopy. Now I am putting you a whole lot of spectrum here, MÖSSBAUER spectrum. The first one, the black one, that is the hemoglobin. Okay, this is the hemoglobin spectrum. What is the function of hemoglobin? Hemoglobin will transport oxygen. Okay, hemoglobin will transport oxygen, and it will transport the oxygen throughout your body. So if you are having a hemoglobin that is having iron +2, and when you are having oxygen, the oxygen will bind to that ferrous ion. So your body is having hemoglobin, so that hemoglobin will be transported by the attaching the oxygen. So you have oxygenated hemoglobin, HbO2. Okay. So your hemoglobin transports oxygen. How you get oxygen? Through lungs, isn't it? From lungs you get oxygen. So that oxygen will be bound to the hemoglobin. So that hemoglobin, oxygenated hemoglobin. And these two spectra, they are shown here. Hb means without oxygen, and HbO2 means with oxygen. Of course, we need oxygen. Now, without oxygen, you will be dead. So, at the same time, it can also bind with carbon monoxide. Hemoglobin can also bind with carbon monoxide. So, if you are going out in the polluted environment, what happens? Carbon monoxide will be there. So, that can also be bound with the iron +2, isn't it? Okay. So, what will be the magnetic state of hemoglobin? What will be the magnetic state of oxygenated hemoglobin? What will be the magnetic state of carbon monoxide bound with the hemoglobin? How it is harmful to our body? How can you find whether your hemoglobin is good, that means whether it is oxygenated or whether it is bound with toxic compounds like carbon monoxide. MÖSSBAUER spectroscopy is the answer. Okay, so you can find whether your hemoglobin is in a good state or in a bad state. That is, no bad state means no carbon monoxide, by MÖSSBAUER spectroscopy. And if you are not aware of this interpretation, you may be just seeing this spectrum, okay, some lines. But if you understand the MÖSSBAUER spectrum, then you will see, okay, this is hemoglobin, this is oxygenated hemoglobin, and this is carbon monoxide. So very simple. Now you see these first three spectrum at the top. The carbon monoxide bound hemoglobin will have a smallest quadrupole splitting and smallest isomer shift. What is quadrupole splitting? The distance between these two lines, right? So this distance between two lines. So this distance between the two lines will be the smallest in carbon monoxide bound hemoglobin. So that will be low spin. Low spin means one electron will be up and another electron will be down. So when one electron is up and another electron is down, magnetism is 0. That means your state of magnetism is diamagnetic. So when you are having carbon monoxide, you are having a diamagnetic sample. When you are having a normal hemoglobin or oxygenated hemoglobin, it is a paramagnetic ferrous state. How will you identify whether it is low spin or high spin? From the quadrupole splitting value. Low quadrupole splitting, low isomer shift implies it is in a low spin state, diamagnetic state, and high spin state means large quadrupole splitting and large isomer shift. So you can easily see here the difference between high oxygenated hemoglobin and carbon monoxide bound hemoglobin. Of course, you can very easily see. The black one is having very small quadrupole splitting, and the red one, hemoglobin, you are having a large quadrupole splitting. Why this is happening? Because of the environment. Okay, oxygenated environment and carbon monoxide environment are different in the ion present in hemoglobin. So from that will be reflected in the MÖSSBAUER spectrum. So you can also see the difference between oxygenated hemoglobin and hemoglobin without oxygen also, isn't it? So the black one is hemoglobin, normal hemoglobin without oxygen. So of course, you will always have oxygenated hemoglobin and hemoglobin, oxygenated hemoglobin, because till you breathe, you will be having oxygen. So that will be there. So if you take a spectrum, you will see HbO2. But if you see HbCO, that is dangerous. Okay. So your blood is polluted with the toxins. So that is one application of MÖSSBAUER effect in biology. I will give you more examples if time permits. So let us go to the next case. Now, one I told you, iron is present in the body as hemoglobin and myoglobin and ferritin. So hemoglobin we have seen. Myoglobin is also similar to hemoglobin. It is also a heme structure. So I am not going further into myoglobin, but we will see the ferritin. Okay. So far, what we have seen hemoglobin or hemoglobin oxygenated, carbon monoxide. Those are all ferrous, Fe2+. Okay. So ferrous state can be found from the table which I have shown previously. You can refer back. So ferrous state we can find whether it is in a different chemical environment. The chemical environment will differ, will change the quadrupole splitting. That is the distance between these two lines. So that also we can find using MÖSSBAUER effect. Now let us go to ferritin. Okay, ferritin. Okay, so from the previous lectures and all, we can easily figure out, or you can interpret this spectrum yourself. Now this is the spectrum taken at 293 Kelvin. Next one is 86 Kelvin, middle one, and the top one is at very low temperature, 11 Kelvin. Okay. So what is the difference? You are having a doublet at high temperature and a sextet at low temperature. I told you in the previous fundamentals, like no, if you are having a 6-line pattern, that means no, it can be ferromagnetic, ferrimagnetic, or antiferromagnetic. That means it is magnetic. Okay. So the previous spectrum, high hemoglobin, HbO2, HbCO, all are only doublet. So meaning like no, they are in the paramagnetic state or diamagnetic state. But now if you go to ferritin, ferritin is a storage protein. Now you take iron, from plants, or you take iron from, as you know, if you are a non-vegetarian, you take iron through flesh. Flesh has myoglobin. Myoglobin has ferrous iron. So you take iron as a non-vegetarian. A vegetarian from plants. Okay. So you take it, and iron 2 plus, that iron 2 plus will be in your red blood cell. So that will be transported, and the iron 2 plus in the oxygen. Now, if you are not anemic, or if your person is good, hemoglobin is good, then no, there will not be any deficiency in the hemoglobin. So our body has some mechanism to supply iron both to hemoglobin and myoglobin. That is no, both in the red blood cells and muscle cells, they require iron. So our body has a mechanism. Body stores iron in the form of ferritin. Okay. So ferritin is nothing but a storage reservoir which supplies our body with iron. Now our body is having lot of iron in the form of hemoglobin and as a storage iron, ferritin storage. So this is only recycled. Okay, so our body recycles the iron within our system, and whatever iron which you take inside is less than 10 to 15%. Only 10 to 15% of iron will be absorbed. Okay, so the ferritin stores iron, and that will be in the form of ferric iron. How will you say that? No, it is ferric iron from the isomer shift values. Isomer shift is less than 0.5 millimeter per second. So that is ferric iron. And what is the state of that iron? It is in the magnetic state. Okay. So that we have seen in this. So ferritin is in the ferric state. Some mechanism to convert the ferric state to ferrous state. Why? Because no, our hemoglobin is in ferrous state, but the storage protein is in ferric state. So our body has a mechanism to convert the ferric state to ferrous state. So you take food, so the food also can have ferrous and ferric. So there will be a mechanism that converts ferrous ferric state. So that is biological part. We are not going into that. So here we will see some iron related disorders. Okay, some iron related disorders. So let us see here. Okay, so our body has iron. What happens if your iron is overloaded? What happens if you are having too much iron? So that is what happens in a disease called beta thalassemia. So beta thalassemia is a disease where you have iron overload, too much iron. So if you give some medicine which can remove that iron, then you can remove that iron using that medicine. And you see here, the bottom one is before treatment. After treatment, you see this has reduced. Okay. So this is in the form of non-magnetic state, which you are seeing here. Okay. So your beta thalassemia is one disease, but there are other diseases. No, maybe you may have old age parents who may be having diseases such as Parkinson's. Okay, so that means like at very old age people may get Parkinson's disease. So neurological disorder. So that if you see the brain pattern, you have iron which is being deposited in the brain of this Parkinson person. Of course, this topic is still continuously being researched. So you have to remove this iron. You can remove this iron by giving some medicine, chelating agents. And if you are anemic, you need iron. So you give iron as iron injections. Okay. So this can be monitored by MÖSSBAUER spectroscopy. So now let us go to plants. Okay, so from biology, human biology, let us go to plants, plant system. So here, this is a rice plant, MÖSSBAUER spectrum of rice plant IR97. And this spectrum was taken from the root of the plant. And the spectrum at 1.4 Kelvin, this is measured, that shows a magnetic state. And from the isomer shift value, we understand that this root has ferric state iron. So they what they did is they grew this rice plant in a ferrous nutrient. So they have ferrous chloride, and they planted this with the rice plant in the ferrous nutrient. But somehow or the other, the plant has the mechanism similar to our human body. Plant has the mechanism to convert the ferrous state to ferric state. So you have the ferric state, and similar to human ferritin, plant also has ferritin. So you can eat them. So that will be iron source. Okay. So root source for ferric state. And not only that, people have studied a lot of plants plant parts, tomato seed, leaves, stem, roots. Then they have also studied the soybean seed, wheat seed, soybean leaf, root, pea leaves, roots. So all those point to a ferric high spin state iron. So they have ferric iron. So from the MÖSSBAUER parameters. Okay. So now let us go to soil iron. Okay. So far we have seen biological iron. Let us go for soil iron. So in the soil we have iron as different forms, goethite. So all these are different mineralogical names which are given. All these are most of them are antiferromagnetic, so they can be also found. Now there are also soil iron which are majorly like hematite, magamite, and magnetite. Okay. So how you get these oxides? Now, initially our universe, they had only hydrogen and helium. After that, stars, they synthesized iron through nuclear fusion. So nuclear fusion, iron was synthesized, and when it was reacted with the oxygen, they form iron oxide during the oxygenated great oxidation event in Earth. So that means like you have iron compounds in the Earth. What are the iron compounds? Hematite, alpha Fe2O3, magamite, gamma Fe2O3, and magnetite, Fe3O4. Now, what is the state of the iron? And if you see soil color, here the color indicates soil color, the rounded one. That indicates soil color. Now, we know nanoparticles. So nanoparticles will be having different sizes. 10 nanometer, 40 nanometer, less than 100 nanometer is a nanoparticle. So you see the color of the nanoparticle. So if your soil is having a nanoparticle of alpha Fe2O3, that is no hematite, from the color itself we can understand that no, this is a nanoparticle soil of hematite. Okay. So what is the magnetic state of the hematite? So that is antiferromagnetic. So that we see from the single sextet which you see here. So this is the bulk state. So bulk state color light brown color, and as you move towards smaller size, it becomes darker. So this spectrum you see 6-line pattern. So that is alpha Fe2O3, that is hematite. And if you are going to magnetite, magnetite is also present in the soil. So that will show a two, that because no, that is a ferrimagnet. Ferrimagnet will have two sides, A side and B side. So this two will give rise to two sextets. So one sextet from one side and another sextet from another side. So you have two sextets. So that is magnetite. Goethite. Goethite is also another mineral. So that will also show sextet. That is antiferromagnetic. So you can find not only the state, magnetic state of the iron compound, but also you can also find what is the size, particle size dependent magnetic properties. Okay. So now I will go to the next slide, which tells about soil weathering. So I have maybe only one more slide. So soil weathering. So when you are having a soil which is goethite, okay, so it can be due to weathering, the size can become very, very small. Okay, so it is a big particle, and weathering will reduce the particle size. Then the magnetic state also will change. So that is what we see here. Okay. So we can find what is the soil, what is the oxide compound. It is magnetic state and your size dependent property. Okay. So now let us go to spectrum from a paddy field. So this was paddy field soil. So you see they have taken soil at different depths. Okay, from the surface. When they saw the soil surface, no, that was somewhat dark brown color. And when they dug at some depth below 40 centimeter, it was somewhat light brown. Okay. And when they went below 45 centimeter, the soil was black in color. And when they took the soil and when they took the MÖSSBAUER spectrum, they saw different states of iron. But at the surface, they saw most of ferric iron. Ferric means no, one electron is removed here. Ferrous means Fe2 plus, ferric means Fe3 plus, one electron is removed here. That means oxidation. Okay. Oxidation will remove the electron. So at the surface, no, there will be more oxidation. Okay. So you see that the oxidation has given rise to more ferric, and the color also will change. And when you go down, it's a reducing state. That is more of ferrous iron. That you can see from the spectrum. You see the ratio of the intensity between the middle two lights. So that will give you the ferrous ferric fraction. Okay, so quantitative analysis also is possible. So when will you have a reducing condition? When you are having more of organic substances or more of silicates, then it will be having a reducing condition. So you have an oxidation condition at the surface, reducing condition at the below. This is not universal. This is from one paddy field taken near Japan, near Tokyo. So there, no, they have volcanic soil. So at the bottom, they have most of silicates. But in our country, it may be due to organic content. Okay. So with this, no, we have seen that no, soil may also have iron in different states, and body also have iron in different states. And you can find the phase, you can find the magnetic state of this system. So in summary, I have covered magnetic behavior, local magnetic behavior in Fe-based compounds. Fe-based compound means no, iron can be in hemoglobin, it can be in myoglobin, it can be in iron oxide as hematite, magnetite, megamite, and other oxyhydroxides. And this can be identified using MÖSSBAUER spectroscopy. So I thank you all for this participation, and thank the organizers for this session. Thank you.
Thank you, sir. Thank you for your outstanding lecture. We deem it a great honor to listen your lecture, sir. Thank you.
Thank you.
Dear participant, this is the time for you. You can ask your question in the chat box. Otherwise, just raise your hands. We will allow you to ask question directly. Sir?
Yes.
Sir, Dr. M. Selvi from Kutralam has raised her question in YouTube live chat. Is low quadruple and spin nature is related to polarity of solvent?
It is nuclear. It is not related to the polarity of solvent. It is a nuclear phenomena. So let's say no, if your sample is having iron, okay, and if it is in the form of a compound, then according to the environment of iron in the compound, the quadruple splitting will change. Okay. So if it is, that means no, it should be bound. The iron should be bound to the lattice of the compound. So it can be a covalent compound, metallic, or it can be ionic compound, but it should be bound, and it should be in a form of a solid. That is very important, because now why we need a solid is because no, we have seen like no, mass. The recoil is inversely proportional to the mass. So if you are putting the sample in a solid, then it is strongly bound, and the lattice mass will be giving the total mass. So the mass will be very large rather than a free atom. So if you have a free atom, mass will be very small, only single atom mass. So that is not helpful. So your sample should be only in a form of a solid. That is an important criteria. And if you have liquid sample, then you have to freeze it and make it in the form of a solid. Then we can have the spectrum, and then we can have observe the MÖSSBAUER parameters.
Thank you, sir. Glory ma'am, now you can ask your question.
Okay, Justin,
Yes.
it's a new information to me that new elements are being formed by nuclear fission. My question is, at what rate new elements are formed in the universe?
Actually, no. If you see, 13.8 billion years ago, the universe they formed through Big Bang, and after that, after Big Bang, whatever electrons, protons, neutrons, they formed within a few minutes. Okay. So then after that, within hours to 1,000 years or 1 lakh years, within that time, galaxy and other things form. Okay, so that means no, all the elements they form as the universe cooled, and like no nuclear fusion. In a fusion, the elemental formation rate it varies according to the star. Like no, in our sun, the sun is a star, so there also no you have nuclear fusion. So hydrogen and helium is the first element which is formed. It is producing new elements. So as the stars grow older and older, you get iron. Okay, so that may happen in millions of years. So according to the mass of the star, it may happen in millions of years. So it depends on the, not in minutes or seconds. So
Okay, thank you, thank you.
okay.
Thank you, Justin.
Okay.
So one more question.
Yes.
How are the nanoparticles used in the elucidation of compounds?
Who are the nanoparticles?
Used in the elucidation of compounds.
No, nanoparticle. See, nanoparticle compound means like no. So let's say like you are having iron oxide. No, it is a compound. Okay. So iron oxide is a compound. So that compound can be in the form of nanoparticle, or it can be in the form of a bulk state. Okay. So if you are probing using MÖSSBAUER spectroscopy, you are probing the compound first thing. Okay. So it's a very good question that know how you are finding the difference between the compound and its nanoparticle state, which I have not addressed in today's lecture. Okay, because no, that is a different topic, nanoparticle topic, which I can talk tomorrow. Because no, it depends on the energy state of the system. As your particle is very big, it will be having a different energy, different thermal energy competition. And when you are having very small size, the thermal energy will be different. So that will give rise to difference in the MÖSSBAUER spectra. So from that only we can find the difference between the compound in the bulk state and the compound in the nano state. Okay, so there is no distinction between the compound and nano. Understand? There is distinction between the compound in the bulk state and compound in the nano state. So that is my answer.
Thank you, sir. One more question.
Yes.
Though antimony isotope 2 has qualities similar to iron, why it is not studied elaborately?
Okay, I will go through that slide. Okay, antimony 121, isn't it? It's studied, right? SB. Now, why? Well, look, the answer is like no. Unlike antimony, iron is present in most of the biological system, Earth, everywhere. Okay, so the fraction of, so that comes from the formation of our universe itself, you know, from the nuclear fusion. So the fraction of elements present in the Earth, the volume fraction, so that will be determined by the nuclear fusion. So how much amount of element is present overall, that depends on the nuclear fusion. So iron is present in most of the biological systems and Earth compared to antimony. So that is why now it is being extensively used. So you can use antimony, but you need compounds, many compounds, so that we can study it extensively. So if you have a compound which you have antimony in it, we can use it, but no, compared to the cost of the maintenance cost and other things, no. If you have isotope, it will be it has to be maintained, so we require samples, otherwise no, it is not useful. So but iron, tin, we have a lot of samples which can be used every day. Okay. And another one is, one difficulty with the antimony is the half width. Now you see, half width means like the spectral resolution. Now you have 6-line pattern. Okay, you have 6-line pattern, double line pattern. So if your width is very large, both the lines, 2-line or 6-line, will be merged together, and you cannot distinguish different features. So your half width has to be also minimum. So your half width, if it is too large, then what happens is, your resolution will be affected. So you cannot identify the spectral components separately. So that will be also affecting your properties. That means you cannot extract a lot of details from the spectrum. So half width has to be also small, and we need compound. Although natural abundance is 57%, which is high, although we have high half-life, 76 years for SB, half width is large, and also we don't have sufficient compounds for analysis. Over to you.
Thank you, sir. Sir, there are so many questions. I think we will discuss all these questions during tomorrow's session.
Yeah, definitely.
Thank you, sir, for your patience to answer our questions and for clearing our doubts.
Thank you. Thank you. See you tomorrow.
Now I call upon Dr. S. Beulah Jelly to propose the vote of thanks.
Very good afternoon to you all. First of all, I would like to thank our Almighty God to shower His blessings upon. I thank Dr. Sahaya Satish for his inaugural address. I would like to thank Dr. Justin Josephus for his useful and informative talk on MÖSSBAUER's spectrum effect, characters, or its application in biology and earth. Thank you, sir. I extend my thanks to our secretary, principal, HOD, and my dear colleagues. Today's webinar in a grand success. I extend my heartfelt thanks to Dr. Serena Margaret, our IQAC coordinator, for her moral. Once again, I thank and I wish you all a great ahead. Thank you.
Thank you.
Thank you, ma'am. Dear participants, this is the time to end today's session. We have noted your questions that will be discussed tomorrow during the tomorrow's session. I request you to join us on tomorrow sharply at 11 o'clock for the second session on magnetic nanoparticles and biomedical application. Thank you.
Thank you. See you tomorrow.
Dear participants, if you have filled out the attendance form, you could leave the meeting. Thank you.